Hello guys! In this video we are going to talk about two tools in order to calculate limits. One is the monotonicity of the limit, sorry for the word, it's very dangerous, and the sandwich criterion. Both are important. In fact, they are somehow related. Let's see the objectives of this video. The objective is to review the idea of limit. We will calculate limits all the time, and we will apply and try to understand the sandwich criterion in order to solve indeterminations. Okay, what do we need? What do we need in this video? Basic algebra and pre-calculus ideas. They are all needed, but as you will see, it's not really difficult what we are going to do. Also, as usual, perform algebraic simplifications and limit evaluations. This is something that we will need during the video, and I will try to at least speak slowly when we come to this part of the video. Okay, let's work. Let's suppose that you have two functions, in fact, three functions. We are going to call these functions f, g, and h. All of them real functions, okay? And we are going to consider one real number that we are going to call a. What is this strange word, monotonicity of the limit? Okay, what does this mean? Let's suppose that the function f is less or equal than the function g. What does this mean if we are talking about functions? That means that f is, imagine that I have a function in front of me, so f is above here and g is always below, okay? G comes here and f is coming here, okay? So f is, my bad, g is going up and f is going down, okay? So we have a function, one is upper and one is slower, for any value in the domain of these functions. Then, if this happens, the limit of this function when x approaches a is less or equal than the limit of the function g when x approaches a. So, it's like the inequality is still true when we apply limits. That makes sense, because if f is always lower than g, the limit of this function should be lower than the limit of the upper function, okay? But we needed to prove it, and mathematically it has been proved. Okay. And what about the sandwich criterion? This is a very important tool in order to solve indeterminations or in order to calculate limits. In this case, we are going to consider three functions, and this is the key idea. The function f is smaller than g and g is smaller than h. So it's the same situation as before, that you have h, g, and f. Okay? What happens if the initial function f approaches L, the function is going to a value L, h is going, or the limit of h is also L, then what we can say in these cases is that g is also going to L. That makes sense. Imagine the situation. The upper function, imagine the upper function is going down to 3. The lower function is going up to 3. And you know that the middle function is always in the middle. So this function should go to 3 again, okay? So that is the sandwich criterion. If you, or imagine that you are walking with two friends. One friend is here and another friend is here. Okay, let me just put it more together, okay? And they are walking by your side and they are going like this, closing your path. Then you will hit them, okay, not punch them, but if you keep walking and your friends are going in front of you and you are all the time in between your friends, you will go the same way. So this is the idea behind the sandwich criterion. Let's see an example. Okay, look at this nice example. We have the limit when x approaches 0 of x squared times sine of 1 over x. Perfect. We need to calculate the limit. What happens here? If we try the substitution directly in these cases, we change x by 0, 0 squared is 0, and when we change here the x by 0, we obtain sine of 1 over 0. 1 over 0 tends to infinity. What is the value of sine of infinity? 0, for sure, it's something we can understand, but sine of infinity doesn't make sense. We cannot say it's infinity. Sine, as you know, and we will see in 5 seconds, sine is a periodic function. It's always going from 1 till -1. So what happens when we move away is still between -1 and 1 going up and down. So I cannot say that the limit of sine of infinity exists. It doesn't exist. I don't know which is the limit. So we don't have an indetermination in here. I don't know how to solve this limit. Sine of infinity doesn't exist. Does this mean that this limit multiplied by x squared does not exist? No. In fact, the limit exists. How can we solve it? Let's see. Oh, by the way, this is the representation of sine of 1 over x. As you can see, it's going up and down. Take a look to this. It's always between 1 and -1, as you can see. It doesn't matter how fast it's going up and down. The key point is that's always between -1 and 1. Okay, so when this happens, we say mathematically that the function is bounded. Okay, it's between two values, and it can do like here. It's going up and down many times, and getting closer to 0 is going up and down faster and faster and faster. Okay. Anyway, it's bounded, and this is one of the key points of this sandwich criterion. Okay, so how are we going to work with this? Again, information. I just told you 2, 3 times, 4 times that sine is between -1 and 1. It doesn't matter what I write here inside. Sine is always between -1 and 1. Do you want to put an exponential function between parentheses? Perfect. Sine is going to force the solution to be between -1 and 1. So this is always happening. In this case, it's 1 over x. Fine. Okay, no problem. So what we have here is the sine is always between -1 and 1. This is an inequality. What are we going to do? We are going to multiply everything by x squared, as you can see here. Okay, so x squared times -1 is -x squared. This function sine of 1 over x multiplied by x squared is the same, multiplied by x squared, and 1 multiplied by x squared, the same, x squared. Okay, perfect. So what do we have? We have three functions. I was pointing 6. 3 functions. Minus x squared, this function in the middle, and x squared. In the previous slide, we just call it f, g, and h, or something like this, okay? So the key point is you have 3 functions. What happens if we apply the limit to these 3 functions? We have the following. The limit of this function when x approaches 0, this function only, okay? The one on the left, it's 0. The limit of the upper function, x squared, when x approaches 0, is 0 again. So the limit of this function in the middle, it's going to be 0. Again, it's like this is going to 0, this is going to 0, and the one in the middle should go to 0. This is the sandwich criterion. Okay? We have been able to bound this function by 2 functions that both tend to 0. Do you want a picture to see this a little better? Here you are. Okay, this is x squared function. This is minus x squared function, the green one. And the function we were trying to calculate the limit is the one painted in blue. As you can see, the function is always between minus x squared and x squared. So whatever the function is doing here is going up and down, as you can see. It's limited by this function. And as you can see, when we approach 0, this function is tending to 0. Be careful, because the previous plot we showed you was only sine of 1 over x. Okay, in this case it's x squared times sine of 1 divided by x. The function we were trying to calculate the limit. So guys, this is the key point of this method, the sandwich method. Okay, here you have another example, and I'm going to solve it really fast. We have still a function x and a trigonometric function in here, sine cube, cosine cube. Okay, sine, it's always between -1 and 1. If we cube this value, it's still between -1 and 1. Okay, so this is always happening. Cosine is always a function between -1 and 1. If we calculate this function cube, it's still between -1 and 1. If you don't believe me, take a calculator and try. Take a number between -1 and 1 and cube this number. You will see that it's smaller. So this is happening. Then if we put it together, sine cube plus cosine cube, if both are between -1 and 1, we can say that they are between -2 and 2. Remember that sine and cosine never cancels at the same points. So you can improve this bound, this number, you can just make it smaller, but okay, we are just trying to make sure this function is bounded, okay? 2 and -2, it's fine. So guys, this function sine cube plus cosine cube is between -2 and 2, okay? Because we are adding the limits, the extremes of the intervals, okay? If we multiply by x, all the three functions, the inequalities hold again, and we got that -2x and 2x are the extremes, the functions. And in the middle, we have the function we wanted to calculate the limit. Perfect. The limit of this function when x approaches 0 is 0. The limit of this function when x approaches 0 is 0 again. So, guys, what is going to be the limit of everything in the middle? 0. Okay? This is, sorry, I just need to write it here, as you can see here. So the limit of this is 0, because the limit of the two functions on the borders are 0. The plot of this function is more or less the same. As you can see, this is the function -2x, 2x, -2x, and the function is in the middle. It happens as before. So what we have seen in this video, we have applied the Sandwich theorem, Sandwich Criterion, in which is used in order to solve some limits. And we have seen some examples in which this Sandwich Criterion has been applied. I think this is a very interesting slide and video, and it's going to be applied many, many times in your life. Thank you for your attention, guys.